Swayam Prabha. Digital India. Educated India.
In this lecture, we will discuss about the methods developed for predicting protein secondary structures. In the last class, we discussed about regular secondary structures. What are the regular secondary structures? Alpha helices, beta strands, turns, right? And the irregular structure we can call as coil, right? How the alpha helices are formed?
By I and I plus 4 bond.
Right, by the hydrogen bonds between NH and CO groups, right, in the main chain, right, I and I plus 4, right, this alpha helix. Then we have two different types of helices. What are the two types of helices? 3-10 helix and the N5 helix, right. Then the beta strand, right, you can also see the hydrogen bonding pattern between the NH and CO groups. There are two types of beta strands, one is a parallel and the other is anti-parallel, right, and you can see the difference in the hydrogen bonding patterns in the parallel and the anti-parallel beta strands. Then we discussed about turns, right, three different types of turns, and type 1 turn is quite frequently occurring, right, in protein structures. Then we discussed about Ramachandran plot, right. What is Ramachandran plot?
Plot between psi and phi.
Plot connecting phi and psi, right, and he used the two dihedral angles, phi angle and psi angle, right. How many atoms are required to get the dihedral angle? 4 atoms, right, because it is angle between two planes, right. Atoms 1 to 3 are one plane, 2, 3 and 4 are another plane. So, the angle between these two planes, right, that is called dihedral angles, right. So, here in the protein main chain, you can see the two types of dihedral angles, one is phi and one is psi. Phi is a rotation along N and C alpha, right, N C alpha, right, and psi is a C alpha C. So, another one, that is the peptide bond. So, Ramachandran, he tried to use these atoms, right, at the hot spheres and see the rotations which are allowed, right, which avoid the steric hindrance. So, based on that, he identified the regions where the alpha helices are populated, right, as well as where allowed regions for the beta strands. So, he developed the plot, right, and that plot is called the Ramachandran plot. Then, if you know the structures of proteins, right, based on the hydrogen bonding pattern, Hobson standard, right, say developed algorithm. Which algorithm? DSSP, right, dictionary of secondary structure proteins, to assign the secondary structures for each residues. Then if you have the experimental data, then we can utilize the information to develop different models for predicting the secondary structures. Right, there are several methods we discussed, right. So, one of the earliest one, that is based on the statistical analysis. Swayam Prabha, first he tried to analyze the preference of amino acid residues in each secondary structure. Which is the values he developed? Propensity, right. How to get the propensity values?
So, there will be division of,
right, first for the any residues, right. So, in any specific conformation, right, alpha helix divided by Ni, number of residues in the protein, right. Then you can see the N alpha, that is the number of residues, right, this way. So, this is for the any residue I, here this is for the whole protein. If the any residue I it prefers to alpha helix, then it will have higher values, right, depending upon the total number of residues in alpha helix. Is it correct? So, likewise you can get the value for the any specific residue. This is only one is this is for the I stands for 20 residues, right, you can get the values for 20 residues. From that information you can see the residues, right, whether the propensity is more than 1 or less than 1. If it is more than 1, then it is preferred in alpha helix, if less than 1, it is not preferred in alpha helix. So, today we will discuss about the other methods. I discussed about the 5 different methods I mentioned. What are the other methods? Based on information theory, this is called the GOR method, and hydrophobicity profiles, multiple sequence alignment, neural networks, right, and the consensus method, right, the join methods, you can say that. Okay, this lecture we will discuss the different other methods to predict the secondary structures and the performance of these methods. We will do the Chowan-Bassman method using statistical analysis. you can identify the segments, but the accuracy is about 60%, 55 to 60%. So, here they considered the propensity of each residue to be in any secondary structure, either alpha helix or beta strand. Now, with that information, Garnier, Ostagrove and Robson, right, they tried to use the information for the central residue as well as the neighboring residues. Why it is required? Because there are some segments, say any pentapeptides or hexapeptides or even tetrapeptides, the same peptides they can adopt different secondary structures, right. For example, if you see a segment A, E, I, V, K, they can be in helix, they can also be in the strand. In this case, if you use this segment, the high propensity in helixes and strand, this can be difficult to distinguish. So, Garnier they try to get the information for the central residues as well as the residues which are occurring nearby the central residue. So, they collect the information, for example, if this is the central residue, they consider the propensity of that particular residue isolation in helix, for example, and see the neighboring residues, about the propensity of the neighboring residues on both sides of the central residues. So, they derived some sort of frequency matrices and use the information for prediction, right, because they use several information, they call this theory as the information theory, because they develop the method based on the information of that particular residue. They consider central residue and they use 8 neighbors from left side and right side, right. This number of neighboring residues depends, we can use any window length and see finally which window length provides the optimal highest performance, right, then we can fix it, right. You can use it for 3, 5, 7 several window lengths, right, and can optimize to get the window lengths with the highest performance. So, they use 8 neighbors, with 8 neighbors what will be the window length? 17, right, because 8 plus 1 plus 8, right, this is the central one, this is on the left side, this is on the right side, right, N terminal, C terminal side. So, 17 residues and they consider 4 different states, right, they consider helix, strand, turn and coil. So, 4 different states they considered. How they derived the information? So, they developed a formula to obtain the information content, for example, I is information content for any secondary structure, right, and any particular residue, right. So, here you can see any residue I, this can be any secondary structure, for example, this X, this can be helix, right. So, preference of that particular residue in helix over the same residues which is not in helix, right. This is the negation, there is which one is the residues which are not in the particular secondary structure. So, how to get this information? They use this particular formula, that is logarithmic of the probability of any particular residue to be in helix, right. This is for example, if you take the helix and the probability of the residue which is not in helix minus, because this is considered only for that particular residue. Now, we have like Chow and Fassman, we have to normalize with the whole protein. So, in this case the whole protein they take the residues in helix and the residues which are not in helix. So, for any residue with any particular secondary structure, they try to use the information that whether that residues, right, prefer to be in a particular secondary structure over the other secondary structures, as well as that secondary structure over other than that particular secondary structure. So, here you can see this SSI is a secondary structure at a position I in the sequence, and X is any secondary structure, they can do it for 4 different secondary structures, right, helix, strand, coil and the turns, and AA stands for any amino acid residue, right. You can use this equation to get the preference of any residues. So, how they derive the probability, right, which information is required to derive the probability? We need experimental data, right, because if we have only the sequences, right, if you know only the input sequences, then we do not know whether the residue alanine prefers to be in helix or strand, we do not know. In this case, we need experimental data. So, they collected the experimental data with known secondary structure information. For example, the structures are known then you can use the DSSP, it can take the hydrogen bonding information and assign secondary structures. DSSP uses 8 classifications, but we can simplify into 4 classes based on by combining all the helices as one helix, like alpha helices, beta pi helices and the 3 helices makes one group called a helix. So, they consider the proteins with known secondary structures, right, with the secondary structure assignment, right. Then we know the assignment, right, we know the sequence, and for each sequence we know the secondary structure assignment, right, particular residue belongs to helix or strand or coil or turn. Then we calculate the frequency of each amino acid in each of the window positions. For example, if you have the window position 17, what is the preference of residue at x, x minus 1, x minus 2, x minus 3 and so on. Likewise, x plus 1, x plus 2 and x plus 3. So, they have 17 residue positions and calculate the frequency of each amino acid for each secondary structures, right. So, they can develop some matrices. So, you can see the 17 by 20 matrix. Here 17 stands for
window.
these are positions, right, 17 positions, and 20 stands for 20 amino acids, right. They can calculate. So, now they use this matrix, right, to calculate the probability as well as the information content, because this matrix contains information about the preference of any particular residue at different positions, 17 positions, right. So, this matrix can be used to obtain the probability of any new residue to be at any particular position, that depending upon the secondary structure. So, now they calculate total information content for each state. For example, take helix, they use this information, what is the preference of that particular residues to be in helix compared to be not in helix. Then do the same for strand, and you can do the same for the turn and the same for the coil. Then we will, how many values we will get? 4 values, right. If you have the 4 secondary structures, helix, strand, turn or coil. So, we get 4 different values. Here you will get x1, x2, x3, x4, and they take these 4, and from this which one is the preferred secondary structure? The maximum. So, maximum of this x1, x2, x3, x4, right. This will give you the preferred secondary structure, right. This is the principle used in Garnier's method. Okay, I will explain with one example. For example, if you have a protein with 1800 residues or a set of proteins with 1800 residues, 810 are in helix and 990 are not in helix. That means 990 are spanning into different secondary structures, either strand or coil or turn. Then you take in a particular alanine. So, there are 300 alanine, right. This for example, right, this is not exact number, this I put for example. So, 210 are in helix and 90 are not in helix. Using this information, we can derive the information content, right. For example, the probability of particular alanine in helix, right, this is alanine in helix, right. What is the probability? Totally how many residues? 300 alanines, right. We are talking about alanine. So, with 300 alanines, how many alanines in helix? 210. So, this you can calculate the ratio, this will be 0.7. Then you can see the same residue alanine which are not in helix, right, which is not in helix, this is negation. So, you can use it, how many alanines are not in helix? 90, right. So, therefore, 90 divided by total 300 residues. So, here you can calculate the probability of alanine which are not in helix, that is 0.3, right. Now, this is for a particular residue, then go with the full residue, full proteins, right, all the residues, right. So, here if you take any secondary structure helix, how many residues are in helix? 810, right. If you take 810, so normalize with the total residues 1800, this will be 0.45. Now, the how many residues which are not in helix? So, you can say 990 divided by 1800, this is 0.55. We use this information, right, to get the probability of alanine to be in alpha helix. So, this is called the information content. So, you can see the probability of alanine in helix, which is given as logarithmic of 0.7 by 0.3. This is for alanine, and here this is for the whole protein. So, now if you calculate this is equal to 0.847 minus this logarithmic is minus 0.2. So, if you subtract then finally we get the value of 1.047. From this number we can say whether this alanine prefers to be in helix or not. So, it prefers to be helix or not?
Yes.
Yes, right. If the value is more than 0 then it is prefers to be helix, if it is less than 0 it is not to prefer helix. For example, if you have 300 residues, 300 alanines, 150 in helix and 150 is not in helix. Likewise 1800 you can put 900 in helix and 900 in not in helix, right. For example, if you put this is 900, this is 900. Here also if you put 150, 150. So, then what is the value we get? Logarithmic of this value will be right 1, right, minus ln of 1, right, this will be 0. So, if it is equally preferred, it is not just 150 150, if the ratio is same, right, it is not the exactly same number, right. For example, here 100 and 200, likewise here also if you see the ratio of 2:3, right, they are fine. So, if you do this then we get the value of 0. This will tell you that for if it is randomly distributed, that means the distribution is same in the full protein level as well as any residue level, then we will get value of 0. So, if it is more than 0, right, then we will get this is the preferred ones. If it is less than 0, right, you can see it is not preferred in particular secondary structure. So, here I show the matrix, one of the examples. So, this is one matrix for the alpha helix, that you can see this is an alpha helical conformation. So, this is the central position J. So, how many window lengths they used? 17, right. So, you can the value is 1, 2, 3, 4, 5, 6, 7, 8, likewise here also 8. So, 8 plus 8 16 plus central one, this is equal to 17, this varies from J minus A to J plus 8. For example, this is the sequence A I K T S V, right. So, if we take this is a central residue J, this is J plus 1, this is J minus 1 and so on, right. You can see the 7 residues this side and 8 residues here and 8 residues there. This is a matrix. If you see the matrix, we can see the preference of some specific residues. For example, to the jth position, right, which residues are preferred in J. So, if you see a plus, that is preferred ones, you can see plus value is here, right. So, this plus value corresponds to alanine, this is 65. So, here this 14, this corresponds to valine and here 32, this corresponds to leucine. So, you can see the glutamic acid here, this is glutamic acid. So, this is 78 glue. So, from this one which residues are preferred at the central position? Alanine, valine, leucine, glutamic acid. This is similar to the propensity obtained by Swayam. Yesterday we discussed, the previous class we discussed about the propensity of residues, right. We could see the preference of these residues, say glutamic acid, alanine, valine, leucine, they prefer to be in alpha helix, right. In this case the propensity is agrees with the Swayam method. So, the data seems to be fine. Now, here they added more information regarding neighboring residues, for example, J minus 1, J minus 2, and see some cases they do not have any preferences and some cases you can see the preferences. Say glycine is not preferred at any position, it is totally random. So, we see alanine is preferred at the J as well as other positions, and some cases you can see the preference at some positions are not in the other positions. So, we can use this matrix to get the information. So, how many matrices they derived? This is for helix, 4 matrices, right, one for helix, one for strand and turn and coil. So, now we have the sequence. So, this amino acid sequence and how we obtain the information content using Garnier and how they transferred the data to predict the secondary structures. For example, if you take the central residue, this threonine. So, these are the different windows, you can see 17 residue windows. So, if you from here to here, right. So, there are 17 residues and you substitute the values from the table. For example, if alpha helix for T is central one, what is the value for threonine? T is here, this is central value, this is equal to minus 26. right, they put minus 26 here. Then take this J minus 8, right, J minus 8 is which residue? Methionine. So, go with the methionine, methionine is here, this J minus 8, this is 10, put the value 10, this is J minus 7, J minus 7 is valine. So, if you see here the valine J minus 7, that is equal to 0, that is equal to 0. Then go with the J plus 8, J plus 8 is lysine. So, if you see the lysine, what is the 3 letter code for lysine? LYS, right, it is here. So, lysine is here, so this value is 0, right, so it is 0. So, now we have 17 values for the 17 positions, right, that is the difference between Garnier and Swayam Prabha use only this 309, right. So, now get the values and sum up all the numbers, then we will get the value of the any window length, right. So, this is not the correct one. So, this for example we put plus 4, right, this is for example. So, if you add up these numbers, right, finally for example if you say the value is plus 4. Now, this prefers to be alpha helix, but we do not know whether it prefers alpha helix compared with other secondary structures. For example, if you get the beta sheet to 15 or 20, right, then that means the preference for beta strand is more than alpha helix. So, in this case what we have to do? We have to repeat for different secondary structures. This is for the helix. So, we have to do for the strand, coil and turn. So, we get 4 numbers. So, if among the 4 numbers choose the best and assign okay this residue is in alpha helix. Likewise, you can assign the values for all the sequence and we get based on the preference we can assign different secondary structures, and at the end we can do some n corrections, right. For example, there are 6 or 7 residues which is continuously predicted helix, in between there is a strand, then we can take this whole segment as an helix, that we can make some n corrections compared with the experimental data, right, to improve the performance of the method. This method also can predict with an accuracy of about 65%. So, then the other methods, so we can talk about the hydrophobicity profiles. So, what is the hydrophobicity profile? We discussed the earlier classes. What is hydrophobicity profile? It is a plot connecting the amino acid residues with respect to hydrophobicity values. We can use any hydrophobicity scales. We discussed about a particular scale, right. Here you can see the hydrophobic residues have more values and the polar residues have less values. So, when you plot these values, right, we can see a pattern, right. They identified some specific patterns for helix or strand or coil or turn. As we know, the helices 3.6 residues per turn, and if these residues are in amphipathic, right, spanning in 2 different phases, right, then 2 in one phase and 2 in another phase, based on that they derived a specific type of patterns. This can work only if the helices are amphipathic in nature. If the helices are not amphipathic, then we cannot see this pattern. In this case, you can the methods will fail, right. In this case, we need to add more information, right. But if the helices are amphipathic in nature, then they can easily identify the helical segments based on the patterns. Generally, in the full all protein structures, about 70 to 75% of residues are amphipathic, right, the helices. So, they could be able to identify these segments. Then we go for the beta strand. Beta strand, there are 2 different types of beta strands. Some beta strands it is completely buried, right, because the residues which are buried are in highly hydrophobic in nature. So, mainly if you compare to the helices and strands, strands are more hydrophobic than helix. So, these residues which are strand they are highly hydrophobic. And second one, the beta strands are also in amphipathic in nature. In this case, you can see 2 phases, and one phase you can see the hydrophobic residues and the other phase you can see the hydrophilic residues, right. If it is in amphipathic nature or the exposed beta strand, you can see a pattern which are shown in this figure, right. Okay, this is the pattern you can see. On the other hand, if the residues are in the buried, right, and adopt the beta strand conformation, you can see a pattern which are shown in the figure D, right. You can see most of the residues which are highly hydrophobic. So, now if you have the patterns for helix, there are 2 different patterns for the strand based on the location of the strands, whether it is in helix or whether it is not helix, is whether in the exposed beta strand or it is the buried beta strand. Now, there is another case, that is for the turns. Turns are generally hydrophilic, like like loops because accommodated with the polar residues, right. In this case you can see a stretch of residues which are less hydrophobic. So, they made these type of graphs based on the known information and the physical basis of how these proteins fold and what are the preference of these different residues in secondary structures. This is not the statistical analysis, it is based on the characteristics of the residues in protein structures. So, if you have any sequence, right, for example, if we have the sequence, we can make a profile, and if you have the profile, then from that profile you can identify the regions which have any of these patterns. Now, if you identify any specific patterns, then you can say okay, this could be helix and this could be strand and this could be the coil or the buried beta strand or exposed beta strand and so on. This is one way. There are also different methods which can be used for predicting the secondary structure based on the average hydrophobicity, right, because this is a single residue hydrophobicity, and you can see some such of residues as we discussed in the earlier classes. If there are one residue which are having different value, so then you do not get the patterns, the pattern will lose. In this case you can get the average values and try to use the average value for predicting the secondary structures, right. So, I will explain how to do that. For any sequence, for example, if you have a sequence, you can make different window lengths. For example, if you take window lengths of 8 residues, take 1 to 8, 1, 2, 3, 4, 5, 6, 7, 8, and the value is equal to I equal to 1 to n hi by n, hi by n. What is hi?
Hydrophobicity.
This is hydrophobicity value. So, you get the for each residue we have the value, it is here, assign the values and add up the values and divide by n. So, n equal to this segment, this 8 residue means n equal to 8, right, you can do that. So, we get the different values, you can use these values to predict secondary structures. How to do this and how to assign these segments? In this case we see a protein, and if you get the amino acid sequence, it is possible to see whether this residue contains more alpha helices or more beta sheets or it is a mixture of helices and strands. How to do this? If we have a sequence and we have the pattern, right, this is a pattern for the helix, and see how many the segments which has this pattern, right, take any sequence and make a plot and see how many segments we have this type of patterns. Then already we discussed about the preference of residues, Swayam method. So, we know that some residues are preferred in alpha helix. If you take a minimum of 4 residues, that is corresponds to 1 turn, and see all the 4 residues are accommodated with the preferred residues like alanine, valine, glutamic acid and so how many segments you can get the preference of residues and how many overlaps with the particular profile and the preferred residues. If they could get many patterns, then we can see this protein is mainly having lot of helices. In this case it is fine to identify the helical segments instead of doing all the secondary structures, this is first one. And the second case, they will also do the same pattern for the strands and see how many segments contain exposed beta strands and buried beta strand and use as Swayam parameters. So, we know the preferred residues in beta strand, take only preferred residues and see a segment of 4 residues and then see how many segments you can identify using preferred residues, then we get the number of segments. Comparing these two, if it is highly dominated by helical segments, we see the protein contains mainly helices. If this contains mainly more number of beta strands, right, and we can see okay, this protein contains mainly beta strands, and some cases you will have both 10 strand segments and then 15 beta strands helical segments. In this case you can see this protein contain the mixture of both, right, this is how we will see. Then if we can see a protein which is dominated by helices, then we see that there will be several helical segments. So, to identify the helical segments, what to do? First we get the window length of 8 residues and construct a plot. Okay, you can see these are 2 different examples for 2 different proteins, right. So, here x axis is the sequence, 1 means that means 1 to 8, average of 1 to 8, 2 means average of 2 to 9, and the y axis is the hydrophobicity value, average value. And if you make the plot, you can see there are several peaks, right. several peaks, and if you see these peaks, some of them are very high from the average. For example, this is high peak, and some peaks which are here just the low peak, just above the average, low peaks. So, if you see these two peaks and compare the known structures, you see there will be a longer segment with the corresponds to high peaks and shorter segments of helices in the lower peaks. So, then we see, for example, if this is a region with 251 for example, then we can see that this is a means for 251 to 258, this belongs to helix. With the lower peak, for example, this is 202, this corresponds to shorter helix, say 4 residues, so this is 205. Likewise, we assign the secondary structures, and then we can make the modifications to refine the end segments based on the preferred residues in at the n position and the C positions, as well as the patterns where they have right this type of patterns. From that you can identify the regions which belong to helical segments. So, what we have to do? First we have to see whether the proteins are dominated with the helices or dominated with the beta strands or contains both, right. How to do that? Take the 4 residue segments and see how many segments you can identify using preferred residues as well as the patterns in helices. Check for helix, check for strand. For example, helix has 25, strand has 2, then this protein belongs to the alpha helix proteins, predominant with alpha helix. If beta strand is 20 and helix is 3, then we can say these proteins mainly dominant in beta strands. If helix equal to 10, strand equal to 15, right, or vice versa, right, then you can say it contains both, mixture of that. If it is a helix, then we deal with the helical segments, we do not bother about the strand. So, get the average profile, make into two groups, one is high peak and low peak. High peak stands for longer segments, low peak stands for the shorter segments, and we can find the incorrections, make the helical position regions. So, this is an example for the beta strand. So, here we use the window length of 4 residues, because short beta strands are frequently occurring in protein structures. So, this way we take 4. Again to make this plot and see there are several peaks. So, each peak represents a beta strand. For example, in this case it is 1, 2, 3, 4, if it is 4, then 4 to 7, that residue is 4 to 7, because 4 residue segment. This corresponds to beta strand, and then we can make the incorrection based on the preferred residues in the N terminal or the C terminal as well as the patterns, right. If you have any patterns, then you can extend the pattern till the pattern ends. So, likewise we can make the incorrections to identify the beta strands. So, now if it contains both helician strands, right. So, we have made the figure, one for 8 residues, which one is for 8, this is for 8 residues, right, and you can see the small one, right, this figure, okay, this figure, that is for the 4 residues, one is for the helix, one is for the strand. So, then we see the patterns, many cases it is distinct, one is here, one is helix is here, and the strand somewhere. So, helix and different distinct places. So, if do so, we can discriminate the occurrence of helices and strands, we can see some overlap between 4 residue and 8 residue segments, then we can get the values and compare the numbers and say whether this can be a helix or the strand, right. We can get this segment and see the average value, based on the average value we can decide whether this can be a helix or this can be a strand. So, now there are three different ways based on the classes, so you can predict the secondary structures using hydrophobicity profiles.